Okay, I'm going to share you the screen with the result of this. Can you see the screen, people? It's a Excel table.
Yes, doctor.
Okay, so I just want to show you these are random numbers. So we're going to start by group 3. Who is group 3, people? Group 3.
Barba, Sayo, and Zamora.
Okay, and then we're going to group 6. Who is group 6?
My group, Dr. Lopez Angeles.
I don't have tildes. Then I'm going to go to group 8. Group 8.
Freire, Pincay, and Jimenez.
Who?
Freire, Pincay, and Jimenez.
We're going to group 4. Who is group 4, people?
Estudillo en Ramón, doctor.
Then we'll go to group 1.
Hidrobo, Delgado y Zambrano.
Then we're going to group 2.
Gutenberg y Vega.
Army.
Gutenberg y Vega.
Then we continue with group 5.
Manrique, Matías, and Matute.
And close with group 7.
Carrillo e Íñiguez, two person the group.
Okay, that's it. So I'm going to let you share the screen. Security, so you can share the screen. Okay. Okay, let's go on. Let's start by group. What's the group? Hey, Barba, Sayo, and Zamora, go on, please.
It's not in full screen.
Right now?
Yep. Okay,
Okay.
so good afternoon. We are the group number 3, and we are going to work with the fishing vessel Rafa. So this ship was lengthened the last year, but we are going to work with the ship before the lengthening, because we found that it's interesting to know why the ship was lengthened the last year. So the main characteristics are the following. The length is 40 meters, the beam is 8 meters, the depth to main deck is 5.51 meters, the draft is 4.50 meters, the crew is 25 passengers, the autonomy is 30 days, and the velocity is approximately 10.1 to 13 knots.
So for the Lions plane is showing this part. We have the stations, but we are thinking to get more stations to develop better results and get a better 3D model. If we talk about the distribution plan, we could see the tanks, the compartments, and the ship holds. And all of them will have to define the loading conditions as showing now.
Finally, in this project, we'll analyze 4 loading conditions. The first loading condition is with the departure from the port, with the tank of the 100% and the fishing holes 0%. the second loading condition is with the arrival of the fishing point. When the tank is 50% and the fishing hole 0%. And the third loading condition is with the departure from the fishing point with the tanks is 50% and the fishing hole 0%. And finally is with the right the port with the tanks 0% and the fishing hole at the 100%.
One thing, when you present the loading conditions, okay, try to mention the expected total weight, okay? Because, for example, in this case, I cannot see which one has the largest weight, okay? Usually the first recommendation, for example, if a ship moves a lot, the first recommendation is to make it larger. Because when you increase the size, you increase the mass, the inertia, and of course the acceleration is reduced. So it's a good idea for me to have a good, that's information is good. That's what I was expecting from you. But in this case, please give me the values of the, now, something else, okay? You mentioned a range of velocity. The thing is that I need one velocity that you're going to analyze, right? Because usually when you increase the velocity, there are two things that happen, okay? Remember, the roll damping coefficient increases, but also there are other things that also change. So so what velocity are you going to use?
I think that the speed is one, the 13 knots.
The largest, okay. So that's the one, okay. It is probably interesting that, right, maybe you remember this from ship resistance and propulsion, but when you have a full load, probably we are not going to reach 13 knots. So, for example, it would be very interesting, right? For example, if you try one of these loading conditions, full loading conditions, you accept that you're not reaching 13 knots, and you could do this analysis, full load with only 11 knots of velocity. The other you can do with lower and high, with lower displacement, but with higher velocity. In that case, we can convert these four loading conditions, okay? And which is very important is you have to start thinking about what are the parameters that you are going to evaluate. Okay, good. Let's go on in the next one, Miss Group 6. Thank you. You can stop sharing the, okay. Go on, Lopez and Galarza.
All right, my partner is going to share the screen with me. Okay, so we are group number 6, and we are going to analyze the preliminary design of a 1,630 meter cubics of oil capacity of a fishing vessel. This is our project in ship design, so we are going to analyze that for for this subject. So the next slide, please. So we're going to do a little introduction, talk about the owner and the requirements of the ship and the main dimension. So the ship owner is the engineer Douglas Wingler. He works from Astinaver, and the requirements are that we have to have a whole capacity of 1,630 meters cubic. The speed is 15 knots, and autonomy of 45 days. The next one. We have done already the linear regressions and optimization, and we have obtained these main characteristics. And we already have done the 3D model and rhinoceros. That's what we have until now. In the next slide, let me see. Yeah,
Yeah,
we already put.
Okay. The hydrostatic calculations for the GMP is 0.22 and the block coefficient are the 0.62. And the conditions calculations for the temperature for the same 100% and the second fishing ground 50% and return for 10%. Thank you.
It's going to be interesting. If you have two fishing vessels, it's going to be very interesting if what we can do is this, okay, people from these two groups, and you can talk each other, and what we can do is when you present the results, you can try to present somehow the similar parameters. So at the end, we are going to be able to see, I mean, what's the difference between these two, because there is a large difference in size, right? So it's going to be very interesting to learn from these differences, okay?
Doctor, and what parameter could be a good idea, like the...
I was thinking on that. In the case of fishing vessel, one nice parameters could be, but I don't know if we were able to calculate that using MaxSurf. But it would be very interesting if we could calculate the reduction in velocity or increment in resistance because of the waves. It will be very interesting. Okay.
All right.
Another thing that could be very interesting is that, for example, when you oscillate like that, right? Okay, when the aft end comes up, the propeller could be a little bit outside the water, right? When the propeller rotates, the water resists the rotation, right? But when you have suddenly outside, the air, okay, offers a very much lower resistance. So you will have an sudden increment in acceleration. And then when it goes inside the water again, it's just, again, the resistance increases. So probably there could be some torsional problems in the propulsion systems. So it could be very interesting if we could get into that, okay? Okay, that's the amount in time, be patient, next week, amount of in an hour that the propeller race gets outside the water. But more or less that could be, but we can talk about that next week. Okay. Okay, let's go on now to group number, who's next? 8. Group 8 people?
Yes.
Okay, so good afternoon, everyone. We're group number 8. And this is the ship that we are going to work with is a tugboat and it's called Tramwayas 2. It belongs to the Equestivas company, actually known as Sam Towage. These are the main dimensions of this ship. It has a length of 34.95 meters. It has a leg between perpendiculars of 31.77 meters, a beam of 9 meters, a depth of 4 meters, a draft of 3 meters, and a velocity of 12 knots.
Good afternoon. My name is Taylor, and the other characteristics that this tugboat has is the more important. The main factor of this is the boiler pool, and this one have 50 tons. And about the capacities of the tanks, we have the fuel oil tanks that have a capacity of a total of 29,259 gallons. And the fresh water, 9,624 gallons, and lube oil, of 400 gallons.
Okay, hello everyone. For the last part, we are the share screen the propulsion of the system of the ship. We have the seven 715 RPM. The main engineer, we have two Caterpillar in 3.606-inch voltage in B cylinders. We are interested in choose and the main environment to operate to in this the high significant height of the weight. We are interested in study the response for in this zone in the performance of the ship, especially in the manta. We have 1 meter the significant height and the place colors and the minimum value the 0.57 meters.
These values for significant height, what did you get them? But because that changes with the sea state, that's the maximum values that you can expect in those areas, I'm asking?
I search in the card.
Yeah, but you have to be a little bit more careful with that, okay? Because what I see is, please, you have to include that information in here. Okay, so the source, it's very important. And also, as I said before, okay, if I give you, for example, sea state 3 or whatever, okay, then you go immediately and you can determine the significant height. But if you give me a significant height, that means that that's correspond to a certain sea state. But it would be a good idea if you specify that and then add the sea state that you are expecting in these areas. Okay, the reduction here is correct, or because if you say that this is a real ship or you are designing it?
No, it's the real one. And according to the...
I'm sorry, I didn't get it.
Yeah, it's the real one. And according to the technical memory, I don't know if that's correct. That's the year production.
Okay, it could be correct, but it just calls my attention because usually at this well, it could be, but check that number because they are, if you have 750 divided by 1.8, that gives you around 400 RPM. Yeah, could be possible, but it's a little bit high to me. Okay.
Okay.
Let's just check that. Good. Now, again, for this type of vessels, you have to look for in the literature to see what parameters you need to calculate in order to judge the response of shifting waves, right? Because usually these talks, they do not work far away from the coast, right? So, but it's a good idea if we could see in the literature what type of parameters should we calculate in order to evaluate this. Okay, and something for everybody. Okay, it's a good point. Okay, let's suppose that we can evaluate this ship. We can calculate the acceleration, response, whatever. Okay, what is that? It's always to compare. There are certain tables. I'm going to present one next week from PNA. But if you could find up-to-date information, that would be quite useful, right? So, for example, these are the acceptable values in this or that parameter for this type of ship. Could be useful. So you calculate yours and you check against that and see, okay, this ship is moving too much or whatever. So that's something that you need to find out from the literature, each group. Okay, good. Let's go to group 4. I can hear you.
Yes, doctor.
Go on.
Good afternoon. Our project of design is a preliminary design of a coastal patrol vessel for 23 crews.
Agenda. Introduction, main dimension, ship characteristic, and prototype and model. Introduction. A coastal ship does many activities. Among them it is responsible of the stewardship of the water and wells and preserving of species. Offshore inshore patrol vessel or coastal patrol vessel is a part of the territorial navigation and is proposed to take care of the interest of the country. The main dimension is length 47.8, being 7.27, speed 25, crew is 23, draft is 1.71, and depth 4.35.
Other characteristic of our ship is the autonomy for 3,000 nautical miles for the propulsion system is a water jet, and the minimum speed that requirement or sponsor is 20 knots, and the construction of material is the aluminum. Well, we have for the analysis, we use the prototype of a Cotecmar in CPV 46, and our model is the other side, and the lot condition is when analyze is that 100%, 50%, and 10%. The route of our ship is Guayaquil or coast, Ecuadorian coast to Galapagos and return. Thank you.
Again, when you mention the loading conditions, it's a good idea. This is a recommendation for everybody. When you present loading conditions, it's a good idea that you said, okay, 100% or consumables or whatever, but you have to include the total weight of the vessel so we can compare, right, the loading conditions. If the loading conditions are too close, we cannot expect much of a difference, right? But if the loading condition is very different, that means that we should expect, okay, we could expect some interesting results, okay? Since this is a military vessel, probably there will be much information about standards and things like that. So it's going to be interesting to see what you will obtain. You mentioned that it's similar to the one designed by the Colombian Navy.
Yes, doctor, because of our design, we have to do take a prototype for a parametrizer, or new vessel, and we see the information of the Cotecmar vessel CPV 46. This is our prototype.
Okay, that's fine. What I'm asking is that do you have any information from them? Because we can compare the results with theirs.
For dynamic information, I don't have, only for the construction and distributions.
It's always a good idea. That's something that we should have as our methodology of working. You calculate something, and at the end, you start saying around, is there any result with which I can check my results? It's always something that we should always do, right? If you calculate something, keep in your records. So you calculate it, do new calculations, and go back to your records. If you have nothing, you try to check with somebody else in order to see if your results make some sense or not. Okay, good. Next, that was group number 4. Let's go to group 1.
Okay, good afternoon, everybody. We are the group number 1, and our project is design of 16 passenger yachts with X-boat that sails in the Galapagos Islands. Our group members is Delgado Jonathan, Zambrano Paul, and who is talking to you, Kelly Drogo. The agenda for today is first the description of problem, the introduction of what is an X-boat, the main characteristics, and the navigation route. Okay, according to the owner requirements, this is the description of the problem. The owner requires the design of a yacht that allows to the passengers do diving and recreational activities while they are navigating through the Galapagos Island. The main characteristics is an X-bow. This is the main difference from the projects due in the past, which will generate greater comfort. And in a specific way, the owner's requirements, the ship has to be an autonomy of 7 days. The capacity has to be 16 to 20 passengers, and the length has to be between 35 and 40 meters.
The X-bow has a tapered shape with different volume distribution, as well as the section angles, resulting in a piercing effect in the weight. Also, this reduces the impact and pitching loads. Comparing the volume with the conventional bulbous shapes of another ship, the X-bow has more displacement and volume, which means that that space can be used for more area for the rooms of the passengers. The shapes of the X-bow distributes the force of the waves more uniformly along the surface of the bow. This allows of the ship to remain more stable to climatic conditions. Also, this improves the comfort of the passenger and the tripulation.
Okay, about our yachts. The main dimensions are length 36.96 meters, beams 8.25 meters, depth 3.25 meters, draft 2 meters, velocity 12 knots, and the area habitability 220.56 meters square. Okay, the navigation route according to the onwards requirements is in the Galapagos Island, where the sea state is 4, when the weight height is 1.9 meters and the weight period 8.8 seconds. Wind velocity is 19 knots. Okay, with this information, we pretend estimate the vertical acceleration in order to improve the comfort of this ship. Thank you.
Just one quick comment. Could you post the first slide, for example? To be careful with the typing, because this information is public, and we have to be careful. One before. You go back one. You present the first slide, please. For example, here in the second line, the word judged. I think the T goes after the CH, isn't it? It's correct. I have doubt. I think it's YACHT. So you have to be careful with that. Okay. In this case, you have to worry about the RMS of the, or not RMS, the MSI, motion sickness index. Okay, so we can evaluate the effect on the passengers. Definitely, that's the main interest here. One thing that you presented this video showing that the ship is supposed to provide an improvement in response. Well, let's evaluate that. Let's see if you can calculate the response, and hopefully that will be able to satisfy the requirements. Now, when we talk about requirements, did the ship owner mention any specific requirement? Mr. Delgado or anybody else?
Yes, the specific requirement was the passenger have 60 passengers. The
Yeah, but
capacity.
what I'm asking is what about to evaluate, for example, let's suppose I'm asking you to design the ship, right? But I have to tell you, okay, I don't want my passengers to get sick in sea state 3. That means that I demand from you that the MSI would be less than, say, 20% in 3 hours in sea state 3. That's a requirement for the design. Did the ship owner propose any specific requirement, restriction for the design in this aspect? No?
No, for that aspect, no.
So yeah, we should. Okay, well, at least we should try to eventually end up with some idea that how good the response it is in waves. Okay, good.
The owner requirements didn't talk about these requirements, but we are considering the stability criteria in order to get the roll motion to.
This is ship dynamics. This is ship dynamics. Ship dynamics means the response in waves. Usually the stability criteria are statics. This is dynamics. But anyway, group 2 people, group 2.
Yes, sir. Okay. You can listen me?
See, yeah.
Yeah, okay. Good afternoon. We are the first slide. Yeah, okay. Good afternoon. We are Liliana Vega and Anita Medina Gutenberg. The project we developed in ship dynamics is the pilot board. A marine pilot board is a vessel that is specifically used to carry helmsmen or marine pilots from harbors to ships that need piloting or vice versa. The type of the board that we will work on in the final project has the following main characteristics. The length is the 15.7 meters. The crew, the crew is the 2 person and the passengers is the maximum to 6 person. The velocity is the 27 knots. Next, please.
And then finally, this board is intended the cost of the continent and the island, the Galapagos Island, and therefore the analysis of the sea state is 3 to 4, and web period is 7.15 and 8.18, and web height is 0.8 meters, and 1.89 meters, and speed with the speed is 13.15 and 19 knots. Thank you.
Yeah. How many loading conditions are we going to consider?
In this moment, I don't analyze this condition. Don't have.
Yes, the people is the many conditions. The minimum people is 2 people, and the maximum is 6. And we vary the velocity.
You vary the number of persons. Yeah, there's not much of a difference in weight. Yeah, probably the best is to change the velocity. But the thing is this, okay? In max surf, see, the problem with this ship is that it's very, very fast, 27 knots. That means that it's going to plan.
Yes.
The problem with that is that it's going to be above the surface. Or not above, but just very close to being above the surface. What's the problem with that? Or not? What's the problem? The problem of using max surf to analyze that is that max surf is intended first the first intention to use max surf is to employ it or apply it to displacement ships. You try to apply it to planing boats. The results, I don't expect them to be very good. So I have a problem with that. It is possible that the results from max surf are not useful to you. So what we can do is this: we can try to apply these results, but up to the fluid number at which max surf makes some sense. I'm sure it's not going to be 27 because the fluid number for that is going to be very high. So probably you have to accept that the analysis go up to a certain velocity, which is below 27, because otherwise the results from max surf are not going to be accepted. Okay.
I have a question. We can try to work with this model, but because I developed this ship in metallic construction, but we can select other ships.
Okay. Now let's use this. But for example, do you have the ship lines of the ship?
Yes.
You have the total weight of the ship?
Yes.
GM?
No, not yet.
That's something we should worry about, because remember, for example, these small ships, it's a good idea if you consider waste from the bow and front waste from the beam in order to get roll response. But for the roll response, remember, GMT is very important.
Thank you.
No problem. Group 5, please.
Hello.
Go on.
Good morning. We are in group number 5, and we're talking about the process about the fishing vessel by the sardiner catch. This is the Violeta 3.
Now, for the main dimension and characteristics is the length is 46 meters, and the beam 95 meters, depth is 488 meters, and draft 371 meters. And the stern volume is the 376 meters squared, and the crew is the 25 persons, and propulsion is the
1,911 HP, and velocity is 11 knots.
Next, we have the distribution plane of the chip. The chip has 6 holes, 3 holes to port and 3 holes to starboard. Hole 1 for port and starboard has 72 cubic meter, and hole 2 has 48 cubic meter, and hole 3 has 68 cubic meter. Next slide. Okay. This chip is composed of 2 full tanks, two fuel tanks, 1 oil tank, and 1 waste tank. This is the description of my chip.
Well, this is the condition we are to analyze. The first condition when the port is paired, and the second condition to analyze is when the ship is fishing, and the third condition is when they return to the arrival at the port. Thanks.
Okay, and do you have, for example, the displacement at each of these loading conditions?
No yet, doctor.
Okay, but please, do you have the lines of the ship?
Yes,
yes. The lines.
Yes.
Yeah, well, for the lines of the ship, you can estimate the displacement, assuming certain loading condition, a certain draft. GMT?
Yes.
How come you have the GMT and you don't have the displacement?
Okay, right now we don't have the information. We don't miss into the yeah.
I need reviewing the
all I need you to know is that yeah, you have to be careful, because if you get behind, you get behind, and we have a very strict itinerary to follow. Okay. Let's go to the last group number 7.
Good afternoon. Our project, we are group number 7. Our project is a bunker ship that sails on the Ecuadorian coast. Okay. You can see the main characteristic on one of them is important are tanks by size, because we are going to analyze in the condition that my partner will tell you later. Okay, this is a 4-line plane that you can see, and we Rhino software, we did the modeling.
Good afternoon, everybody. Good afternoon, doctor. Parents is need to return wait. We are going to apply for the moment 3 conditions with respect to the fuel tank or gas tank and the cargo tank. We transport this petroleum. Therefore, we believe they are ideal for the wave response project. The first condition is about the charging for outlet. Second condition is unloading of a load at one point of the trip. The third condition is with respect to return to the port. 3 conditions that occur with analysis we carry of the indices, full and cargo tanks have more influences in type ships.
I missed it. What was the velocity of this ship, please?
Is
11.5.
In the loading conditions, Can you show me the slide with this loading, with the loading conditions? Condition 1 and 2 are the same, isn't it?
Condition 1 and 3, you can do.
Condition 1 and 2 are the same. Oh, no, I'm sorry. No, you are like this. Okay. Same recommendation. When you present the loading conditions, try to give me the total weight. Okay. One curiosity. Is this ship going to be with no velocity charging a product or something like that?
Yes, the ship is got the product in Panama, but he shared the product in the coast, the Ecuadorian coast.
But he comes into port, or he gets in some place, and another ship comes close to it, and there is some discharging.
No, it's the same ship. They made the old road.
What I'm asking, see, one of the problems, remember, is that when your ship has no velocity, the damping coefficient reduces. So if you have to stay, okay, with no velocity, the ship is going to move a lot. And here, for example, and another ship gets closer, and you try to provide to this ship with certain loading, cargo or gas, whatever, okay? But you are with no velocity, and that means that you're going to move a lot. That's what I'm asking. What's the how it is going to operate? That's what I'm asking. You don't know?
I don't know.
The thing is that if the ship is going to operate like that, you should check that, because that would be a nice condition to analyze.
Okay.
Usually, if you consider that this ship operates only with loading, that's something interesting. Yeah, but it is possible that this ship operates with no load, okay, on ballast. And that's usually a nice condition to analyze, because when you have lower mass, the ship moves more.
Okay.
So instead of, for example, condition 1, 2, and 3, maybe you can change the condition 2, analyze condition 1, 3, and the other condition would be ballast, in ballast. So you have the extremes. You can compare. It's always a good idea.
Okay, doctor. Thank you.
Thank you.
Problem. Okay, people. So this Thursday, we're going to see. We're going to be in the from 1 to 2:30. We're going to have an evaluation, and from 2:30 and on, we're going to have the work at the lab. Okay. The evaluation will be up to last Thursday material. Also, that's chapter 4 and 5, basically. Closed book. I haven't started thinking about the evaluation. I'll do it tonight. And there's going to be probably some short questions and some couple of problems to be developed. Short questions are multiple choice. I don't want to grade too much because I'm very loaded with extra work. Okay, so be ready. And that's it. Is there any questions about this? And from now on, Mondays, Tuesdays will be progress control. So we're gonna have another similar progress control next Tuesday, and then Tuesday after that. Next Wednesday night, 7 p.m., I have invited Professor Trosh, okay, from the University of Michigan to give us a lecture via Zoom. So I need everybody to be there. Say it again. I need everybody to be there. That's in 8 days. So please, is there any problem with that time schedule? No? Then
At
I
what
need
time is, Doctor?
7 p.m.
Sorry, I can't.
7.
Oh, the Thursday.
Wednesday.
It's okay, no problem.
Thank you.
Doctor,
So I need,
some of us have metallics at this hour.
okay, who is the instructor for that?
The engineer in Douglas, Wingle.
I'll talk to him.
Okay.
Or talk to him, ask him in my behalf that please permission to come to this session. As a matter of fact, I'm going to open the invitation to outside the university. So probably people from Astinave will be interested in coming into the presentation. Yeah, but talk to him and ask him if it is possible that grants you permission to come to this presentation. Professor Trosh is a wonderful person, wonderful person. It's an extraordinary scholar. He's retiring. He's finally retiring. He was my instructor some 30 years ago. He's just retiring. And I contacted him and asked him to see if he can give us some ideas of how he sees chip dynamics in the future. More or less, that's the general idea of his presentation. So the thing is that I would like you to, at the end of the session, to ask questions, whatever, believe me. I'll try to be there in order to need some help with the translation, anything like that. But yeah, he's worldly known. It's an expert, really. So it's going to be a very nice idea. Okay. So I really hope everybody should come. Everybody should come. And that's it. Any other question, people? Any other questions? No? Okay. Thank you. You can start recording, Miss.
Doctor.